All right, welcome to the Explainer. Today we're diving into a really fascinating piece of technology, one that takes a tiny component from an old watch and uses it to completely revolutionize the search for energy. It's a story about learning how to listen for the faintest sounds, miles beneath our feet.
So, think about this. How do you actually find natural gas when it's buried miles deep inside the Earth? I mean, it's a massive challenge. You're drilling through solid rock in this incredibly harsh, noisy environment, all while trying to pinpoint these hidden pockets of hydrocarbons. And for decades, believe it or not, the basic methods for figuring out what you found haven't really changed all that much.
You see, the way it's been done forever is they bring up this drilling mud from the bottom of the well, extract the gas from it, and then analyze it in a lab on the surface. Now that whole cycle can take several minutes, which, when you're spending a fortune to drill, is an eternity. The dream, the goal, has always been to have a sensor that can give you answers in real time, right there, down in the well itself.
So here's our game plan for this explainer. We're going to start with the hunt for hydrocarbons. Then we'll get into the wild science of seeing gas with sound and meet the watch's secret weapon. After that, we'll look at the lab in a shoebox results, see how it reads a gas's fingerprint, and finally talk about what this means for the future of exploration. Okay, so let's start by looking at this challenge up close. It really all boils down to that expensive, frustrating delay between when the drill bit hits something interesting and when you actually know if you've struck gold, or, in this case, gas. So, the old process involves all these time-consuming steps. First, a detector up on the surface measures the total amount of gas coming up from the well. If that number looks good, a sample then gets sent to a much slower machine called a gas chromatograph, which separates all the individual molecules, the methane, the ethane, all of it. Every single step adds to that critical delay between hitting gas and the engineers getting the data they need.
And that delay? Well, it created this desperate need for a real breakthrough. And the answer came from this kind of mind-bending field of physics called photoacoustics. It's essentially the science of using light to create sound. Yeah, you heard that right.
Okay, so how in the world does this work? It's pretty wild. You basically zap the gas with a laser. The gas molecules absorb that light energy, they heat up instantly, and they expand. That creates a tiny little pressure wave, which is literally just a sound wave. And here's the brilliant part. Different gases absorb different colors of light. So, by tuning the laser, you can make a specific gas, like methane, sing. And then you just listen for its unique sound to measure how much is there.
But, there's always a catch, right? The microphones they were using to detect these incredibly faint sounds were, well, they were big, and they were clumsy. They were easily disturbed by vibrations and background noise. And that is a total deal-breaker when you're trying to use this tech on a loud, rumbling, shaking drilling rig.
So what the technology needed was a completely new kind of sound detector. Something small, something super rugged, and incredibly sensitive. And as it turns out, the perfect solution was hiding in plain sight, on millions of wrists all around the world.
And get this, the hero of our story is the quartz tuning fork. This is the very same tiny component that kept time in quartz watches for decades. It's this little two-pronged crystal that's engineered to vibrate at a near-perfect 32,768 times per second. That incredible precision is what made our watches so accurate.
Researchers realized this tiny fork wasn't just a great timekeeper. It was the perfect miniature sound detector. The source material calls it a high-quality optoacoustic transducer. Now, that's just a fancy scientific way of saying it is ridiculously good at turning a tiny sound wave, one made by light, into a clean electrical signal.
This little fork is a game changer because it solves all the problems. It has a super high Q factor, which means it rings very purely, like a perfect crystal bell, making it incredibly sensitive. It also vibrates at a really high frequency, so it completely ignores all the low-frequency rumbling of a drill rig. It's also tough as nails, and its tiny size means you can build a ridiculously compact sensor around it.
Okay, so the theory is great, but how does this tiny little fork actually perform when you build it into a real-world device? Well, researchers put it to the test.
So the team took this whole principle. They call it Quartz-enhanced photoacoustic spectroscopy, or QEPAS for short. And they managed to build a fully functional sensor that fits inside a small, rugged case. I mean, we are literally talking about the size of a shoebox. It is a complete portable gas laboratory. So how did it do? Well, its precision is right up there with other common technologies. You can see it's a little less sensitive for methane, but just look at the results for ethane. It hits a sensitivity of 7 parts per billion in just 1 second. That's actually better than the other tech.
And just to put that number into perspective, 7 parts per billion, that is like being able to detect just a few specific, marked drops of water in an entire Olympic-sized swimming pool. It is just mind-blowingly precise.
But here is where it gets really cool. This sensor can do so much more than just detect that gas is there. It has this remarkable ability to read its origin story, to tell geologists not just what gas they found, but how and where it was made.
The secret here is something called isotopes. You see, not all methane is created equal. By measuring the ratio of the rare carbon-13 isotope to the much more common carbon-12, geologists can tell if the gas was cooked deep underground by heat, that's thermogenic, or if it was made by microbes closer to the surface, that's biogenic. And for exploration, that clue is absolutely vital.
And what's so incredible is that this QEPAS sensor is so precise, it can distinguish the laser absorption between the everyday carbon-12 methane and that much rarer carbon-13 version. And remember, carbon-13 only makes up about 1.1% of all carbon out there. Being able to detect it this accurately in real time is just a phenomenal feat.
So, what does a tiny fork from a watch that can hear a gas's fingerprint actually mean for the real world? Well, the implications for finding energy are pretty significant.
The advantages are huge. Because you're getting analysis right there in the wellbore, engineers get real-time data. This lets them make critical decisions in seconds, not minutes or hours. That leads to way more efficient drilling because they can instantly identify the sweet spot of a reservoir.
And this enables a technique that drillers have dreamed about called geosteering. It means they can actively guide the drill bit based on the gas they're detecting, moment by moment. It's like giving the drill a sense of smell, allowing it to sniff out and stay within the richest, most productive part of an energy formation.
And so this incredible technology, born from a simple component designed just to tell time, leaves us with a really powerful question. If we can repurpose something so common to listen for the signature of gas deep underground, what other invisible worlds could this technology help us hear? What other amazing discoveries are just waiting to be found? Thanks for watching The Explainer.